This video is all about logistic regression and its approach. So although the name says it's a regression, but it's essentially a classification problem. Sorry, my bad. Essentially a classification problem. So there are three ways to tackle or approach logistic regression, namely geometric. The second approach is probabilistic, and the third approach is where loss function. Today we will take a look at the geometric approach. Why? Because it's very basic and very intuitive to understand visually. It's always better to proceed with the geometric intuition in the beginning. So what linear logistic regression does, it essentially separates our data points. Since it's a classification problem, so it classifies using a line for a 2D or a plane or a hyperplane for 3D or multidimensional. So in this case we will use a plane and not a line. So line is essentially a linear equation. Line and the plane is essentially a linear equation. But for quadratic, we use a circle or a parabola. So let's not go way too deep into the mathematics. We'll proceed with the algorithm itself. So in order to simplify our logistic regression, we'll assume that our plane passes through the origin. This is X, this is Y. Our plane passes through the origin. This is what we'll assume. Why, I'll tell you in a while. So we all know that the equation of a line is y equals to mx plus c, where mx is the distance of the point, mx is the slope, and x is the point, and c is the interceptum. Similarly, the equation of a plane, this is for a line. The equation of a plane is pi, what is the plane itself. We denote the plane using pi. Pi equals to w transpose xi plus b, where b is the intercept. Just like c over here. So what is w transpose xi? This is essentially the distance of a point from the plane, or di we can say. So di is basically, so I'll show you with a better diagram. Let's proceed further. So this is the line or plane pi, and we know that always there is a normal to the plane, which is w. We'll assume that the w is towards the positive. Here we have the positive points, and here we have the negative points. So the equation of the plane is pi equals to w transpose xi plus p. Actually w transpose xi is di, or distance from the plane to the point xi. So the distance we can further show in the form of w transpose xi divided by the unit vector of the normal. So since it's a unit vector, its value is 1, hence it's just w transpose xi. And so since this is our positive class points and these are the negative class points, positive, and these are the negative, we will use our yi as +1 for positive and -1 for negative. in previous algorithms we have used +1 and 0, but here we will use -1. I'll tell you exactly why we are doing this in a short while. So since this is a unit vector, our equation becomes W transpose xi. So here in our equation of the plane, W transpose xi plus b, where b is 0, hence we will just go with W transpose xi. Our W is also a vector of dimension d dimension, and x is also a vector of d dimension rd. Now what happens is, just like k nearest neighbor, we assume that the data point is, if the neighborhood has more positive points, this data point will also be positive. So this is an assumption that we use for k nearest neighbor. Similarly, we use assumptions in naive Bayes as well, where we say that the features are conditionally independent of each other. So what we do in logistic regression? In logistic regression, we assume that our data set, or Dn, is almost or perfectly linearly separable. If this doesn't happen, we cannot separate it using a line or a plane. Hence, we have to assume that our data set is either perfectly linearly separable. It's a tongue twister, you know. Perfectly linearly separable or almost linearly separable. So let me just redo the diagram once again. This is a line. This is a positive points with green, and the negative points with red. But since we are considering over here we will consider the almost linearly separable. So what we do is we use a data point, erroneous data point here and an erroneous data point here. This is our plane and this is our W, or a normal to the plane. So this side we have the positive plane, positive side of the plane. This is the negative side of the plane. Always remember that. So this line separates the positive from the negative. So any point that lies towards the direction of the normal is a positive point, or classified as positive point, and any point that lies away from the direction of the normal is a negative point. So here arises 4 cases. Point 1, this, where the point is positive and the distance is also positive. Let's just say the point is xi and the distance is di. This is one case. Second case is where the point is negative and the distance is negative as well. Let's just say the point is xj and the distance is dj. And third, where the point is actually negative but it lies in the positive side, hence the distance is di and the negative point is negative. And for this, where the point is actually positive but the distance is negative, or it lies in the negative side of the plane. So we'll take a look how to tackle this, or what exactly happens in the classification of all these 4 cases. So case 1, where the point is +1 and the distance is positive. So I haven't mentioned prior that how it classifies is through the equation is yi w transpose xi. If our yi w transpose xi is greater than 0, that means it has correctly classified. If our if our yi w transpose xi is less than 0, that means it has incorrectly classified. This is what the final outcome of logistic regression is. So we'll bifurcate into 4 cases and we'll see what exactly happens and how it gets classified. So in first case, our point is positive, and the distance is also positive. So yi, that is equal to +1, and di or w transpose xi is equal to positive. So positive into positive gives a positive that is greater than 0, hence correctly classified. For case 2, this point, this where the point is negative and the distance is on the negative side, or it lies on the negative side of the plane. So what do? The distance or the yi is negative or -1. The distance or w transpose xi is negative. Hence our equation becomes yi w transpose xi equals to -1 into something negative that becomes positive, which is again greater than 0. That means it is correctly classified. Now case 3. What is case 3? Case 3 is we have a negative point in the positive region. Hence our point is negative but our distance is positive. So let's see how it goes. So our point is -1 and our distance, di is positive. The equation becomes yi w transpose xi that is equal to -1 into something positive that is equal to negative. This is negative, right? So negative into positive becomes negative, which is less than 1, less than 0. If we draw in the number line, this is 0, this is positive, this is negative. So anything less than 0 is negative, hence misclassified. Now case 4. So what is case 4 is this point where the point is actually positive but it lies in the negative region. That means the dj is negative. So we'll see what happens. Point that is yi is equal to positive but dj is negative, that is w transpose xi is negative. Equation becomes yi w transpose xi that is positive into negative equals to negative, which is again less than 0. That means it's misclassified. So these are the 4 cases that can arise when you are trying to classify using logistic regression, and our sole goal is to determine the plane, exactly where the plane will be, so that it has the best result separating our positive or our one class from another class. So our main target, see, xi and yi is fixed. So what is variable is w, that is our normal, and our interceptum. Here we just consider that it is passing through center, hence b equal to 0, and this is the intercept. These two are variable. So our key goal is to find this two. What exactly? And finally, what logistic regression tries to do is to maximize the summation of yi w transpose xi, because if this is positive, that means more and more points are properly getting classified, are correctly classified, hence we're trying to maximize this. So the equation becomes plane equal to argmax w, where w is the normal, wi, let's just say wi is the normal, or w star is a normal, is the plane star, that means the best possible plane, is similarly the summation of yi w transpose xi. We are trying to maximize this, So this is what logistic regression is in its geometric approach. I hope I have clarified everything so far. If not, you can just comment down below. I'll just, let me explain you in a better way if that's even feasible. Thanks so much for watching. Take care. Have a nice day.